little segment on convergence, okay? So pointwise and uniform convergence are the strongest, but of course, you know, L2 is the most general and easiest to prove, okay? We've already kind of shown that our series solution does satisfy our PD in terms of the boundary conditions, okay? But let's say, let's remember that convergence, okay, helps show that U sub t equals k u x x, okay? So what I did in last lecture, right, is remember that I just plugged U into that PDE, okay? Now, if we take a closer look at that, right, for t greater than 0, as long as we assume that f of x is, let's just say that it's L infinity, it's some bounded function, okay? Then what we can say is that Bn sine of n pi x over L has absolute value bounded from above by Bn, is bounded from above by 2 over L, integral from 0 to L, f of x sine of n pi x over L dx. And this is bounded from above by 2m, right? So whatever the max is of our function, okay? So this implies that Bn sine of n pi x over L e to the minus k n pi over L quantity squared t, right? Each of the terms now in our infinite series for t greater than 0 is bounded from above by 2m e to the minus e k n squared pi squared over L squared t, okay? So that means that this sum, the sum from n equals 1 up to infinity to m, this is our bound on our sum now. This is bounded by the Weierstrass M test, okay? So the solution is bounded, right, for all values of t greater than 0. Therefore, u of xt is equal to n equals 1 up to infinity Bn sine n pi x over L e to the minus k n squared pi squared over L squared t. It actually converges uniformly for any t greater than 0. So all we need is a bounded function f, and it turns out our solution on the interior of the domain, right? Remember, as soon as we move into this domain, right, we have this infinite series solution where the terms are actually dropping off exponentially. So there's no concern about this being unbounded away from the boundary. The only concern really is the boundedness of our Fourier series right at the initial condition, okay? So so does this work for ut and uxx, okay? And in fact, a term by term differentiation is justified, okay, if the result is uniformly convergent, okay? So for instance, uxx, right, is equal to n equals 1 up to infinity, right? all that's going to happen is that we're going to get these extra terms, n pi over L squared, right? Should we be concerned about those? Well, remember that we still are going to have these exponential terms, which are going to fall off much more rapidly, okay? So we can bound, right, n pi over L squared bn sine of n pi x over L e to the minus k n pi over L quantity squared t by just 2m pi squared over L squared n squared e to the minus k n squared pi squared over L squared t. Okay. And again, we can say that the sum is going to be a convergence series, okay? And we can do that using the m-test, okay? Because this is not going to grow as much as this shrinks, okay? Now we can summarize everything that we've said so far about the heat equation in a theorem, okay? And that theorem says the following, okay? It says that if f, all it has to be is L infinity from 0 to L, and let's say L1 from 0 to L, then u of xt equal to n equals 1 up to infinity, bn sine of n pi x over L e to the minus k n pi over L quantity squared t solves u sub t equals k u x x for t greater than 0, for x living in 0L, right? And then u at 0 and L is equal to 0, okay? Moreover, if f is C2 from 0 to L, and we also have that f of 0 equals f of L equals 0, then u of x0 equals f of x. And finally, u of x is uniformly convergent, okay, which is the strong form of convergence, but we have that strong assumption on f, right? And continuous for t greater than or equal to 0, okay? This is actually not hard to prove because we have nice strong restrictions on f in this particular case, right? We add this assumption here, right? Now, if we don't have that strong of an assumption on f, okay, then we can at least say that u is going to satisfy the PD on the interior, okay, and that maybe it will at least L2 converge to the initial condition at t equals 0, okay? But given the strong assumption that we have, right, remember b of bn is equal to this integration of f against L, right? Remember that we can integrate by parts to get that this is equal to 2L over n squared pi squared times an integral, which we can bound, right? We know that then Bn is bounded from above by 2L, something I'll call m prime prime, pi squared times 1 over n squared. And this implies that the Fourier series, right, is going to converge uniformly, okay? So that's enough of this specific case, okay? I want to end off with